Let's see, first a caveat, I'm not a nuclear physicist. In fact, the only course I ever took in nuclear physics was when I was a senior. This is a junior. What level are you guys? So it's harder now. I took it as a senior in Berkeley from Louis Alvarez. You ever hear of his name? He won the Nobel Prize for kind of the discovery of many of the elementary particles in the bubble chambers. And the class was at 8 in the morning. If you showed up late, you didn't get in. If you were reading the Daily Cal, our rag that they hand out every day, that you got thrown out of class. So life has become easier, I think. Anyway, I didn't know you were talking about burning of the sun. I don't. So I know nuclear physics mostly because it invades everything in physics. So except for a course like this one, but taken as a senior, I've never studied nuclear physics, but it comes everywhere. So I'm going to talk a little bit about a few topics. We'll see when I run out of time, where nuclear physics is kind of born into it, even though it sounds like another subject. So I'm going to talk about three things that are related, kind of, as you'll see if I manage to do it. One is something you talked about. You talked about the burning of the sun, of a star, I guess, last time, which is a good start on what a supernova is. Everybody has heard of a supernova, so I'll talk about that. And when a supernova happens, there's different products of a supernova. One of them that I've been close to is what's called a neutron star. And so I'll talk a little bit about that. And then finally, how neutron stars can be observed in what I do, which doesn't have anything to do with nuclear physics per se, because it's studying gravity, but it does, as I'll try to show you. So I'm going to stick to the nuclear physics elements of this. Some of it's going to be over your head, but purposely, because it'll give you a sense of what people are trying to do in nuclear, have to solve in nuclear physics now. That's kind of hard. So it'll give you a kind of a sense of where it's going. So, as I said, I'm going to talk about supernova, in particular, what's called core collapse. There's different kinds of supernova, I'll tell you that, but what's called core collapse type 2, that's the label given. So you can, if you remember that much, you know what we're talking about. Neutron stars, which are one of the possible products of a supernova. And then I'm going to talk about something that's very new that we've seen, which has to do with the collision of two neutron stars, if I get that far. So let's talk about supernova. Supernova is a word that's used for a whole bunch of phenomenon, which basically have been mostly discovered by people with their bare eyes and not with telescopes, because all of a sudden somewhere, when you look at the stars, something lights up. And of course, telescopes don't look everywhere. They look pointedly somewhere. So it's often discovered by the naked eye. The last one, what we care about the most if we really wanted to understand supernova, other than seeing a thing deep in the universe go flash, is have one close enough that you can really study it, but not so close that it causes trouble, of course. And the last one that was ever observed in our own galaxy is called Kepler, and it's for obvious reasons, and it was observed in 1604. So that's the time of Galileo, basically. And so in 1604 was the last one that happened in our own galaxy. If we calculate from the life and death of stars, an estimate of how often these supernovas should happen in our own galaxy, taking the number of stars there are, we calculate that it should be like one every 25 years. But it's happened, so maybe we're overdue, or maybe there's something wrong with the calculations. Or people think that maybe they happen in ways that are kind of dusty and we don't see them, and so forth and so on. So we're not sure, but there's a discrepancy. It's been there ever since I've been in physics. Anyway, there's two types. The first type, which I'm not going to talk about except to give you the words and tell you why it's important, is called type 1 supernova. And it's a binary star system. So just like the Earth and the Moon, stars going around each other, not necessarily equal size. One of them is what's called a carbon-oxygen white dwarf. That's a kind of star, small star that exists. I won't kind of define it, but it's a category of stars that's small. And it is a companion. So it's a little bit like the Moon and the Earth. And it sucks matter out of because they interact with each other as they go around, and the matter's not tightly bound like on the Earth, so some of it gets sucked from one to the other. and the matter gets sucked to the companion star, to the carbon white dwarf. Eventually it gets too much matter and it explodes. I won't talk about the explosion mechanism because it's not today's. And it happens to be incredibly valuable because every time it explodes, everywhere, no matter where, it more or less happens when it gets to be a certain amount of mass, so it gives exactly the same amount of light and signal, which means it's the best marker we have for what we call a standard candle. That is how far, you can tell how far away it is just by the fact that it got dimmer, because it's going to go down as, as the distance. So that's what's used to measure distance by astronomers for all kinds of different things, but especially for example, measuring the expansion of the universe or the famous constants in astronomy. Almost all use these as a standard candle, a way to get away. I'm not going to talk about them, but that's enough to tell you what they are and how they happen, so you can know what they are. Instead, I'm going to talk about this type because it's what gives the nuclear physics that I want to talk about today. And this is called a type 2 supernova. It's mostly seen in other galaxies. I'll show you a list in a minute. The last one seen in our galaxy is the one I pointed out, 1604. So what is it? Let's go slowly. This is now nuclear physics. This type occurs at the end of the star's lifetime. So you talked about how a star burns. A star burns by the nuclear fusion process. Apparently you talked about that last time. Nuclear fusion first works on the lightest elements, and a star is made out of mostly hydrogen, helium, and then a little carbon and heavier elements. So it starts burning up the light elements, and as it burns up the light elements, some of the mass flows into the center. That's called the core. And if it gets too much mass in the center, that mass gets pulled in. There gets to be an envelope, and the star collapses. That's called core collapse. That's the word that's given. You can imagine that's kind of easy to wave your hands at, but a little hard to calculate exactly what happens. And so when it becomes heavy enough, it collapses. When it collapses, there's a shock wave that creates light, which is what has been seen. It also has nuclear physics. A supernova. It also creates nuclear reactions that give neutrinos. It also creates gravitational effects because it comes in and that gives the thing that I do, which is gravitational waves. So the main thing that, of course, has given us information is light that you see, photons with your eye or with some telescope. And so that's it. These different elements, the different layers, indicate that the light elements are out near the outside, the heavier ones more in the inside. And the fusion process, another way to just think about it is the fusion process burns up the light elements. It can burn up, eventually it runs out of fuel because it can get up to iron, and that's it. There's no fusion beyond that. So, but more dynamically, it's this core collapse. Okay. So the next thing is, what's the features of the light that comes out of the supernova? And this is an analysis of the peaks that come from doing an analysis of the colors and the lines in the light. And the one that we care about for today is this one, type 2. And it has the big lines here. And it's characteristically, say, different than this one. And it's what's called a type 2 supernova. And it is the one that gives all the elements instead of the white dwarf business that I said. So we can tell that it was a type 2. If you ask me, how did I tell whether it was type 1 or type 2? You tell it by looking at these lines, basically. And if you see a pattern that looks like this one, that's a type 2. The type 1s have some subcategories. I won't talk about them today. What I said before is enough. Okay. So there's a supernova. This is a picture of the most recent supernova that's been seen. It's called Supernova 1987A. It was in a star that was labeled as SK 20269, and it's not in our galaxy. It's in an appendix to it that's outside, but not very far outside our galaxy. It was actually seen by an amateur astronomer in the southern hemisphere. So here's a list of the supernova that are best known that have been seen. I don't know if it's a comprehensive list, but from type 2 that have been seen with the naked eye. So not that many, some deep. This is the last one. It's called Shelton because the guy that saw it in the sky was named Shelton. So now you can get your name if you can actually look at the sky enough and see one. And that was seen in 1987. It's called Supernova 1987A, because astronomers always do ABC, even though they happen once every 50 years. They have a scheme where in any given year it's ABCD. So SN 1987A just means it was the first one that year, obviously the only one that year. That one was unique because actually the neutrinos that came from it, which I won't talk about today, were seen in the big neutrino detectors. So it was seen in 2 different neutrino detectors. And that was the first time that neutrinos were seen, which established the kind of physics that the fusion process happened, with the kind of energy that neutrinos, which are a product of the nuclear physics, came out at, what their spectrum should look like, how many there should be, and that was all pretty consistent with this picture of core collapse being due to the nuclear fusion process, and it was important in that sense. This is the brightest past supernova. It's in the Andromeda, and it basically is the most studied because it's so bright that it's still, after all these years, it happened in 1885, but you see the remnants still bright now, and so when new satellites go up and so forth, they often study this one. This is another famous one, 1668, and 1604 was the last one in our galaxy. Okay, what about the first? Where was it seen at the beginning? The earliest recorded observation of a supernova is now given this long number here. Of course, there was no number then. It was 393, and it may or may not have been a supernova. It's debated. But it was seen by the Chinese. In fact, the first 2 on the list were seen by the Chinese. So they were the first to ever recognize supernova. And this is what they wrote. So this is the first one, maybe not the first one seen, but the first writing of somebody that saw something that maybe was a supernova. In the 2nd year of the epoch Zhongping, the 10th month on the day Kuai Hai, a strange star appeared in the middle of Nan Moon. That's Alpha Centauri. It was like a large bamboo mat. This is very scientific, you can see. A large bamboo mat. It displayed the 5 colors, both pleasing and otherwise. It gradually lessened. In the 6th month of the succeeding year, it disappeared. And so that, people aren't sure, but they've actually tried to trace this in recent satellites and tried to confirm, because there was an alternate theory that this wasn't really a supernova, it was a comet. And that people had, because that's not exactly a very detailed technical description. But I think the most recent belief is it probably was the first one ever recorded. And the second was like that. And then the information gets a little better, but you can see they're pretty rare. People who study neutrinos, or like myself on gravitational waves, anticipate that one hopefully will happen in the coming decade or sometime, but we don't know. Okay, so when a supernova happens, because of the fact that it's a nuclear fusion process and there was all this heavy matter in the star that has to go somewhere, it ejects a lot of heavy elements. So one characteristic is that a lot of heavy elements come out of a supernova. And if you go back in time to all the supernovae ever made, not just the ones close to us that we could see, that's been believed to be the origin of the heavy nuclear matter that's like in the Earth. So where did heavy matter come from? The universe is mostly made out of hydrogen and helium. So how did it get in the Earth when the Earth was made? The belief is that it came from the ancient, collapse of stars, made the heavy elements, and they ended up in the Earth. It turns out that only works up to about iron for the reasons that I said, but we have heavier elements in the Earth. Some we like gold, platinum, things like that. And we may have the answer to that, which I'll show you at the very end from our experiment. Or we may not. We just have a good clue that we may have the answer. So, okay. So what happens after this supernova occurs? What are the final product? It's going to be something. Things collapse, so it's going to be smaller than the original object. And depending on how big the star was and the mechanism by the details of how it collapsed, there are different answers to that question. So if it was a light star, it turns out to, for example, make a brown dwarf or something light, heavy. A dwarf is a heavy dead star, more or less. So it's collapsed to some small size, maybe the size of the Earth, but has the mass of the Sun, if it was that size, or so it's been made heavier, not as heavy as what I'll talk about next. The other remnants can be, if the star was really big, it can collapse and actually make a concentration of mass that's so strong that it's what we call a black hole. I can't take the time to talk about black holes today, but that comes from a heavier star. We believe that a star has to be at least 3 times heavier than our sun to make a black hole. We've detected black holes in our experiment up to about 50 or 60 times the mass of our sun. So black holes would come from heavier stars than our sun. And if it's about somewhere like a couple times the mass of our sun, then it makes often, we think, what's called a neutron star, which is what I'll concentrate on because it has the nuclear physics in a few minutes. Our sun can't even make a neutron star because a neutron star turns out to be almost always 1.4 times the mass of the sun. So it's a little too heavy to make it from the sun, but we make it. When you make a neutron star, it's a fantastic object. As you'll see, it's spinning, it gives electromagnetic radiation. So there's a lot of science that's been done once they've been studied. And I'll just mention that. So I mentioned already, this is the evidence, the detector that saw neutrinos. I just have it out of order from this 1987A. A huge vat of liquid scintillator. Scintillator is a liquid oil that's doped with an ingredient that if a particle loses energy, it emits some light. And so this is full of the purest water you can make on the Earth in an enormous volume in order to be sensitive to rare things. With all these photodetectors around it. This is in Japan. And actually this experiment that detected the supernova neutrinos and detected neutrinos directly from our sun won the Nobel Prize in like 2015 or something. And you can see it here. A man, there's no man in the picture, but a man is really tiny in that. They have to use divers to go down in it, and there's a huge purification process to make it clear enough. And this is the data which I won't take the time to explain to you. Okay, so let's talk about just briefly the phenomena of the going from what you learned last time, the sun burning, to making a supernova. This is the part you won't understand, but I want to wave it at you because it's what physicists who do nuclear physics and are trying to understand the burning of a star are trying to do. And I'll just wave it at you so you get some sense. There is no exact answer. So the mechanism of core collapse is what we said. In the end, I don't know if you've used the word, but an important ingredient is what's called the equation of state. If you use that term, okay, we'll forget it for today. But if you have an object and you want to characterize its nuclear physics, like a neutron star, you'd like to characterize it by understanding its so-called equation of state. It's a way to mathematically describe what a neutron star looks like in terms of nuclear physics. The process that goes on is nuclear synthesis, and these are the main kind of technical names that are used. There's something called a P process, an R process, and there's different peaks that people look for to see the nucleosynthesis. And there's what happens to the nuclear matter itself as you go through the process of the sun. And what I'm showing you next is a series of graphs that are the different characteristics that you can measure. And the different curves represent the fact that there are different people that try to calculate it with different assumptions. They don't get quite the same answer. And in the end, that matters because we cannot reliably simulate how a star burns and then explodes. So the best computer programs at Lawrence Livermore Lab, places like that try to calculate what happens when a star burns and don't always explode, let alone the fact that they have all kinds of assumptions. And the problem is that you have different behaviors for different things. This is the radius of where the shock starts. And so it can differ by 10 or 20%. And it doesn't sound like much, but it's enough to affect whether the shock happens. There's a whole series of these different things that, and you see the different names are just different people who use different models, which is what happens in nuclear physics, to try to calculate these, and then they argue at meetings and so forth who's right, but we don't have any data to tell who's right, so it goes back and forth. This is some other parameters. This has to do with how the electrons get captured in a nuclei, and you can see this, in this case, the graphs on here go all over the place, so we're not able to really calculate that. Entropy is always a hard thing to calculate. And I'm just showing you a series of these just to show you the effect. This is the calculations of the electron capture process. And again, the differences are, in this case, about a factor of 10. This is a log scale of two different models that people have in the literature. So they're presumably got some semblance of reasonable nuclear physics put into them. The problem is you can apply what you know about nuclear physics to a new problem like this. The thing has a lot of time-dependent effects that happen. You don't know the ordering in which they happen. And we don't have any data to go back to. It isn't something we can compare with something in the labs. So people model the different pieces of it, like this happens before that, and so forth. And you can get quite different answers. So the capture of the electrons is one that you can see a quite big difference. And just more, this is the impact of the stellar mass itself, and you can just see again the different curves represent different modeling. This one is for a heavy star, I think 15 solar masses. And then you end up with some sort of picture of what happens when the star collapses. So this is the time and the size. It first actually grows in size, and then it gets smaller, and then finally collapses. And all this stuff's going on. It's cooling, it's heating. There's a shock wave, and so forth and so on. And you put all this together in models. And this is a picture that looks pretty good, but you saw what the errors were on it that were quite big. So the purpose of this part of the talk, I don't need it so much later, but the purpose of this part of the talk is to give you a sense that nuclear physics is alive and healthy in understanding something like how a star burns, and it's pretty important because it affects astronomy and astrophysics so much. So it's just one example of the fact that nuclear physics invades almost everything in physics and is there where people are doing things. So I think I said most of what's on here. This is posing the questions. What effect does nuclear physics have on the explosion? The equation of state, which I mentioned, but you don't know yet. The things like electron capture and all this kind of stuff. How does it affect it? In the end, we can't do reliable calculations of the behavior, and we can't yet reliably have an explosion on the computer, which means it's hard to predict things for other kinds of physics, like gravitational waves that I do. Okay, now let's go on. So understanding supernova is, as I said, a very active and important subject. When do I quit? 11? Okay. I'm okay. So it's a very active subject, and all the pieces of it. So we can have final products that are black holes. That's a whole subject. It's basically what I spend most of my life on. The final products can also be neutron stars or brown dwarfs, as I mentioned. And the radiation itself comes out in different forms. I mentioned this too, but let me emphasize it. It can be light or electromagnetic radiation, neutrinos, which is a product of the nuclear reactions themselves, the weak interaction, and it comes out in the form of gravitational waves. So let me say these in words, how they happen. You start with a star, and it actually expands a little bit, and then it collapses, and it goes, and when it is going like that, that's gravitational. What happened is you had the nuclear physics fusion process basically pushing out and holding all the nucleons out. At the same time, of course, gravity is trying to pull them all in. And eventually, when you burn stuff up, what happens when the core collapses is you've collapsed gravitationally. So when you've collapsed gravitationally, it turns out that if that process isn't exactly symmetrical, it emits something called gravitational waves, which is what I do. So that's the last part. And it's the first thing that happens. The star is burning, burns up, it goes gravitationally. When it collapses, all the nuclear physics is happening now in a compressed way. All the nucleons are together in a very small place. And the product of those nuclear reactions that is detectable is what's called the neutrino. Have you talked at all about neutrinos?
Beta decay.
Okay, well, beta decay is an example. So you make some sort of nuclear reaction. The elements aren't stable, so they decay. And all the other products of the decay get absorbed. Like an electron doesn't go anywhere; it can't get out of it. But the neutrino doesn't interact almost at all. So that's the product of those decays that actually escapes from the supernova. So those neutrinos, and I mentioned that those for the first time were detected in this supernova that was just outside of our galaxy. And they actually, there's only 20 or so that were detected. But within those 20, looking at the distribution of energy and the number, it was consistent with the kind of calculations or expectations that you expect if the sun burning really happened by the fusion process. And that's why they got the Nobel Prize, because it proved. We have many theories of things. We may believe them, but finally you need empirical proof. And this was the first proof that what happens in the sun is the fusion process. And so that was a worthy Nobel Prize. And the third one is, of course, electromagnetic radiation. That's the first one, of course. That's what you or anybody looking and sees this star all of a sudden brighten up sees. So those are the three products of the supernova. Okay, so now let's talk about what a neutron star is. And this is a really active subject for nuclear astrophysicists to understand what a neutron star is. I'm going to give you a really simplified picture. So we start with something like the sun, or something bigger than the sun, because the mass of this is 1.4 times the 1.5 they wrote there, 1.4 times the mass of our sun. So imagine that we started with a star that's about twice the mass of our sun. It goes through all of this and it collapses, and its final main product is all the nuclear elements that are left compressed into a small size, and it weighs 1.5 or 1.4 times the mass of our sun. So that's this. It physically, and I won't take the time to tell you we don't know this for sure, but the picture we have is that it has on the outside kind of a crust. And that crust is about a mile thick. And it's what holds it all together, more or less. And then the total diameter is only about 12 miles, so it's about the size of Riverside. So you've taken something that's more massive than our sun, and you've compressed it into a space that's about the size of Riverside, which is a very interesting laboratory, because now you have all these nuclear particles all so tightly compressed that you can try to understand a lot of what happens to nucleons and protons and so forth when they get very close together. And that ends up with terms like equation of state that I talked about, trying to understand what the processes are. The inside's thought to be kind of a liquid, but these are physicists without much information trying to make consistency models of things. But this is kind of a picture you can take away, that you have something about the size of Riverside. It has about a mile of kind of a hard crust, and then inside has liquid inside. In my case, where we study gravitational waves, which I'll come to, we can detect whether this thing is perfectly spherical or not. So if it has little mountains, like a millimeter mountain, we can detect it. But if it doesn't have any of those, we see nothing. So I'll come to that. So now what happens? You make this thing, but it tends to be spinning. So it spins around its own axis, and then it has currents in it, but they may go around a slightly different axis. So it happens that if I have currents going around, there's magnetic fields and so forth, because you have all these particles going around and moving. So they make currents and so forth inside. This is a known phenomenon because we see the results of it. And I'll show you what they are. So they go around, and so what you can imagine is if I have an electron going around like this, going around, it makes a current that goes down the axis. And so basically this will emit radiation along the axis that it goes at. Now, where are we going to see that if we're an observer? Well, it turns out that this thing's going around, but you can think of it like, I don't have sound on this, but like this. Imagine it's a little bit like a lighthouse with a light. You'll see it when that light beam or the beam happens to come past you. And so if you have a telescope that can respond to the radiation that comes out of this, then you see this blip each time it comes around. And the distance between these tells you how fast it's going around and so forth. So you see these little blips. They tend to be in radio. So the radio telescopes is what people use to see these. And again, I think the first observation of so they call this, instead of a neutron star, because it comes in pulses like this, it is a neutron star. They call it a pulsar. So when you read about pulsars, that's just a neutron star where the signal is being looked at and seen as a radio telescope. An example of a radio telescope that people may have heard of is Arecibo, because this big radio dish is in Arecibo, and it was in this famous movie that was made that I can't remember the name of, but somebody might. So anyway, there's these big telescopes just look for radio signals, and if they go around, you'll see this kind of signal. This is just all the numbers. I'm not going to bother with that. Now let me tell you about gravity a little bit. So gravity, I'm just going to talk about briefly because I just want to show you what we can detect from these things. Gravity is something we learned from Newton, but Einstein rewrote it. And in Einstein's theory of gravity, he basically, it's a little more complicated than the product of two masses over r squared that you learned in elementary school. So I'm not going to talk about that, but that's just to show you that. But the main thing is that what he did was integrate space and time together in Einstein's theory. And when he did that, a product of that is that there are something called gravitational waves that come out just like you have electromagnetic waves. And I can't really take the time to go through that for you today, but there's gravitational waves. What do they do? If a gravitational wave goes through you, what does it do to you? It makes you first, or second, a little taller, and then a little shorter and fatter, back and forth between that, at the frequency of the gravitational wave. So if a gravitational wave has a frequency of I don't know, 10 times a second, you'll get a little taller and shorter and fatter, taller and shorter and fatter 10 times a second. You probably haven't noticed that, but it's a little bit like going to the amusement park and going back and forth between these two mirrors, the one that makes you tall and one that makes you fat. And so our goal and what I do is to use that as the key to detecting the gravitational waves that passed you. The trouble is it doesn't make you very much taller. And the distance is actually really small. It's 10 to the minus 21 meters if you're a meter tall. So that's a pretty tiny number. And it's taken a long time to make sensitive enough detectors to do that, but that's not today's purpose. We use something called an interferometer to do that, and that's shown here. Got 5 minutes or what? 15. Oh, 15 minutes, I'm good. Okay, so basically the way you do it is illustrative of how you do precision physics. Measuring a number that's really small is really hard, and it's really difficult to do it absolutely. So we have, for example, how big is a meter, or how heavy is a kilogram? We have a big laboratories and agencies that spend their whole time and reason to be to tell you how much a kilogram weighs or what a meter stick is, because knowing the absolute value of something is really hard. And it's not that they're dumb, it's just hard. Telling the difference between two things that are nominally zero is you can do much more precisely. So that's just a fact of physics. And so it turns out that we have an instrument that's very good at that called an interferometer. And that measures this distance versus this distance. And as long as they're the same, what you do is send light from here, and it goes, split it, so half of it goes down one arm, half of it down the other arm. If the two arms are equal, the same distance, they'll come back at the same time. You invert one compared to the other, they cancel, and your little detector that would see the signal sees nothing. So nominally you see nothing. Now a gravitational wave goes through, which I'm picturing here happening about 3 times a second. And when it goes through, it does what I said, makes it taller and thinner. So it makes this one shorter while this one gets longer, this one shorter when this one gets longer. And so you can imagine when light comes down here and comes back, now they won't come back at exactly the same time. You'll get a little light in this signal here, and it'll be modulated by the 3 times a second or whatever it is. So how well do we have to do that? This is the reason it's difficult. We have to do that to a precision of 1 part, to get to this 10 to the minus 21. We have to do it to a precision of 1 part in 10 to the minus 12, in 10 to the 12, so a millionth of a millionth of the length of the system. So you have to basically do that compared to the wavelength of the light you're using. So that's pretty small. And it turns out that the Earth shakes a lot. So you have to also isolate yourself from the Earth by a factor of 10 to the minus 12. I don't have time to talk about how you do all that, but that's what you have to do. So let's see a picture of an interferometer. Wait a second. Showing you the idea. So it comes back and forth. They cancel. Nothing much happens here. If they get out of line, then light goes here. And then I show it with a wave coming down. So when a wave comes down, you split it. It comes down to the end. Of course, it's a mirror. Comes back, and then it's coming back from the other arm too. If they're back at exactly the same time, they'll cancel, like that's shown, and nothing happens here. If they get slightly out of phase with each other, then you'll start to see light in here, which I'll show here. So as it goes back and forth and creates light, then you measure that here, and that's the signal. That's the idea. And that's the way that a gravitational wave detector works. And this is just a picture of them in real life, ours. They're 4 kilometers or 2.5 miles on a side. There's 2 of them, so we measure the signal in 2 different places, once in Louisiana, once in Washington. Okay. And there's all kinds of signals that you might get for gravitation. I'm going to concentrate on the one that has to do with nuclear physics. But first, if you have these neutron stars, you can get a signal from them alone, and I'll talk about that. Or you can get a signal from the fact that you can have pairs, just like the Earth and the Moon. They come in pairs. So I'll talk about both those slightly. There's all kinds of other signals, just to mention them. We could see the signal from a supernova directly. I mentioned, of course, that idea, but we haven't had a supernova close enough to see gravitational waves. Maybe we will someday. We can look for pulsars in our own galaxy, and that's what I'll talk about. And I'll talk a little bit about this. The last kind of signal that you can do gravitationally is signals from the early universe. And some of you probably have heard of the way we know what we know about the Big Bang and the early universe, which comes from studying what's called the cosmic microwave background signal. This is the low energy electromagnetic signal that satellites look for. And it sees, by studying that in various ways, you're able to see the expansion of the universe and so forth and so on. But it has the limitation that because it's electromagnetic and the universe was very dense when it was young, photons got absorbed. So you have to be at least 300,000 years after the Big Bang itself to start to see anything with photons. So our only way to go back and try to study the early universe now is limited to 300,000 years from the Big Bang itself. And in the future, one can hope to go back to earlier times with gravitational waves, possibly with neutrinos, because they don't get absorbed. So that would be the way to actually, we can't do it now, but the way to actually get information on how it all began, what the first instance of the Big Bang looked like. We can't do that with electromagnetic radiation. So anyway, I'll concentrate on the two that I talked about involving neutron stars today. Okay, neutron stars. So here's a picture of neutron stars that we know about in our galaxy. Our galaxy, we think, by calculation, should have about 100 million neutron stars. We've seen 2,311. So we've seen a small fraction of them. And of those fraction, 10% of them are actually binary, meaning they're pairs. So that's maybe not surprising, since we see, a lot of satellites around the Earth. They're starting to see in exoplanets that they come in pairs, and so forth. So that's the source. This is just the gravity. For the reason that I showed you, they give a signal and they go around, give another signal. That actually turns out to be an incredibly accurate clock, because they do it over and over at the same speed. So this is one of the most accurate clocks in nature, is a spinning neutron star, or a pulsar. I'm not going to talk about this. We can test general relativity, that these can be a source of gravitational waves. I will show you. And as I mentioned, that the information that we can get, for example, in gravitational waves helps constrain this nuclear state that you haven't quite learned about, but what you can think about it is a way to define what the nuclear characteristics are of a compact object like a neutron star. Okay. And this is just a picture of the ones that are found in our own galaxy. Okay. So now how do you look for them? If there's a pulsar in our own galaxy, we saw it's going to be periodic when it comes around. And it's easy to search for the observed ones. We said there's 2,311 of those, so we can go look for signals from those, study them. They're studied electromagnetically. We can look for gravitational waves that come from them. I'll show you that we don't find any with our accuracy. But the right way to look is to look through and try to find the rest of these and find ones that aren't so well established. The ones that can be seen in radio telescopes that are such good clocks. Why are they so good? They came from some star that collapsed so long ago that the final product, although it's spinning, has gotten rid of all its little mountains and so forth. It's very spherical. So if you want to see the effects of effects that are more early in when the neutron star was born, and effects that have other science like gravitational waves, then you have to find early ones. To do that, you can't look for just the ones that are found, but you have to look at the sky. But if you look at the sky, the trouble is the frequency itself of the gravitational wave is modulated by the motion of the Earth relative to the solar system, and the intrinsic frequency then changes. So you can't look for just a single frequency like we looked at before if you talk about a lower one. And the amplitude is also modulated because there's an antenna pattern. So as this thing moves, both the amplitude and the frequency are modulated, which makes it a really hard job to look for them. And as you might guess, it's a huge computing job. The pulsars themselves can come in all different forms. They basically can be accrete matter. They can be wobbling because they're not really, totally symmetrical. They can be bumpy in nature, which would give gravitational signals. So all these are models or hypotheses, and so studying these younger ones, if you can find them, would be great rather than the 2,300 that have been studied so far. So in our case, we've looked at the 200 of the known pulsars to look to see if we could see gravitational waves. You remember there's 2,300. So of those, we looked at the most likely ones. These are all limits. We don't see them. And there's another parameter that happens in a gravitational wave. The frequency is not absolutely constant. It's what they call spinning down. It's slowing down slowly. And so by slowing down, that means it's losing some energy to slow down. And because if you take some energy out of it, like for gravitational waves, it's going to lose a little bit of energy. It's going to slow down a little bit. So what all these dots down here are the fact that the amount of energy that's being lost due to the frequency change is smaller than our ability to measure it. So those we don't touch. Some of them are above, and those we don't see. And so there we can say, okay, what we did is measure something that's a log scale that's 10 times smaller than the amount of energy that's being lost, let's say. And therefore, less than 10% of the energy is going into gravitational waves. That's all we can do at this stage. We don't see any of these. But as I said, these are all a sample of the very old, well-known neutron stars. So, the parameter that we set is this one, which basically tells you how different from perfect sphere have you been able to say this star is, this neutron star. And it's pretty small. It's 1 part in 10 to the minus 8. So it's these things, when they're spinning, at least those known ones, are really very, very spherical. Okay. Now, if we try to look for the neutron stars that are spinning and are younger, so they might give gravitational waves, neutrinos, much more interesting because they've been born recently. I mentioned to look for those is really hard because for every point in the sky, we have to look and trace it as the antenna pattern of our receiver changes and as the frequency changes. And you have to go through all the parameter space that's possible. And if you do that, you end up with a computing problem that's well beyond anything we can do with any computers we have. So we invented something which we call Einstein at Home. Einstein at Home, you can join. It basically borrows from you or steals from you or takes as a gift from you your spare cycles on your laptop or whatever you have. And we use it to help us get enough computing power to look for these. So if you're so inclined, when you go home, look for Einstein at Home and you can join. We found, using our algorithms for gravitational waves, we found new radio sources by this method, about 10 to 20 of them that had never been seen before. So we know how to look, but we don't have enough computing power, and you can't solve the problem for us because we need much, much more. But the amount of computing power that we have from people who have joined Einstein at Home is about 10 times more than we have of our own, so it's pretty good. So I'm soliciting if that's fair to do in a class at Riverside. I don't know. Okay, and then we basically set some limits on these different ones. This is with this Einstein at home, and we set various limits on these. We don't see anything, so I'm going to go on. I only advertise, that's why I showed this. I'm going to go on and end today talking about not just a single neutron star, but a pair of neutron stars. And as I said, it shouldn't be surprising because we have lots of stars that are paired, planets that are around stars, and so forth. So finding binary systems is not uncommon. I mentioned that about 10% of the neutron stars that have been observed in radio telescopes have a binary second star connected to it. So this is the system I'll end up talking about now. We have two neutron stars going around each other, and we managed to detect one of these by its gravitational waves. It was 130 million light years away, which means it happened, what we detected happened 130 million light years ago, but now the signal got to us. And we detected it last year in August. And this is, without any details, the signal. And we detect something we call a chirp signal. That is, this is the time, seconds, and this is frequency. And what happens is when these two objects are going around each other, as they lose energy going around each other to gravitational waves, they spiral into each other and eventually merge. As they spiral in, their frequency gets higher. And so they make a signal that goes whoop, goes to higher frequency as time goes on. That's a so-called chirp signal. That's our signal right there that we measured. I won't tell any more details about that. That's the signal that we saw. The interesting thing is that that's the first time we've ever seen anything that wasn't from black holes, which we can study. They're great for gravity, gravitational waves, but they don't give anything for telescopes. That's why they're called black holes. But these are now nuclear objects, so they should be able to be seen by telescopes. So we saw this, and then 2 seconds later, you'll see here, it was observed in a satellite that looked for high-energy gamma rays. And because they were pursuing something called gamma ray bursts. These are these funny signals that were first found by defense satellites in space that just give a burst of gamma. They're not a supernova, but just a burst. And people had all kinds of theories what they are. But even seeing this with ours, that confirms that one of the ideas is the right one, which is that they come from a binary system when they actually merge and make a flash. So that's what we're seeing. Being two seconds later, whoops, I did that twice. We and the satellite itself can point to where it happened in the sky. So this is where it was in the sky. This is the signal from us, this little one here, for gravity signals. And this is the resolution or the knowledge of where it happened in the sky from the gamma rays, and they overlap. That gave enough confidence to alert telescopes all over the world to look at that piece of the sky right away. You know, some of them looking at radio, some of them looking at different wavelengths of frequencies and stuff. And there's something like 4,000 optical instruments in the world, and more than half of them turned and looked at this place in the sky at that moment in August. And so what they saw, I won't go through in any detail, because that's not what I want to show today, is summarized here. So basically, we saw a gravitational wave signal early. Then the high energy gamma rays, you can see some signals that we're seeing, X-rays, ultraviolet, optical, radio waves, which are still happening now. This is time going on for months. And so everything turned on. And so watching all the different radiations and different frequencies, you can redo the nuclear physics. And a physicist at Columbia University named Metzger had before this happened, one of the phenomenological theories of what happens when two of these neutron stars merge, and had done it in detail, how much energy comes out, what its form is. He called it a kilonova. So, you know, we have a supernova, we have a nova, and this is 1,000 times brighter. It's not as bright as a supernova, but it's 1,000 times brighter than a nova. And so it gives a signal basically called a kilonova. This kind of confirmed that, at least qualitatively. And this is my last slide that I'll show today. And secondly, if you then take his model and one event, you don't really know a rate very well with one event, then you can predict in this case what kind of particles came out when these two neutron stars collided together. And we've had a puzzle in physics, which I alluded to earlier, for tens of years or 100 years, and that is, how was the Earth formed in a way that we now dig down and find gold or platinum in mines? Where did it come from? Gold and platinum are heavier than iron. We can't make it by the fusion process in the sun unless there's some mechanism to enhance it. And you may or may not talk about the R process in here, but there was a process that people guessed might be. So there's been kind of, when we don't have the answer to something in physics, we make up some way that something might happen. So it was made up that it might happen in certain ways and still came from a collapse of a star. Instead, if you now take, how do we know that these elements higher than iron exist? How do we know that? Because we know how to do it in the laboratory. In the laboratory, we make heavy particles by taking some reasonably heavy particle and bombarding it with a lot of neutrons. And then we make a heavier one. And if we're successful, we get to name it and put it into the periodic table. And that's kind of how we did them all. Well, what's more like that lab experiment than two neutron stars colliding with each other? So this is a phenomenological analysis, this is my last slide, of the fraction in yellow of each element that was actually made by the neutron star process, making some assumption about what the rate is from our single event. And you can see favorite elements like platinum or gold were probably in the past made by collisions of neutron stars, not by a supernova. So I think that's my last slide. Yeah. So with that, that's it.
Thank you.